In this video, we're going to look at the concept of the derivative. This is one of the key points of the class, and we saw the idea of it appearing in an earlier section of the instantaneous rate of change. Here we have the graph of y equals f of x. We want to talk about what the slope of a graph is, but we have graphs that are not straight. So we look at the slope of what we call the tangent line. We're going to use for the time being, look at these being a very simple idea, and taking the idea of a tangent line being something an intuitive concept, we see the tangent of the graph being here at the point connected roughly in this region. For the point connected here, the tangent line would be along this curve, show the straight line shown here. So the idea is pretty straightforward here. We want to use the idea of a tangent line to discuss the idea of directions of motion. So if this were a roller coaster or something and you were flying along here, if you were to be released off the tracks, your path would naturally follow this direction, assuming no outside forces. But again, at the moment you see right here, the direction you're going is along the path of this arrow. And the point we see right here, the direction you're going is along this arrow here. Now, the issue here is pretty simple. To find the slope of a line, we need 2 points. And all we have at this point is actually one ordered pair. We have a, f of a. But to do slope, we need 2 points, a y2 minus a y1 over an x2 minus an x1. So we definitely do have half of it. We have either this pair or this pair, but not both. So if we were to talk about 2 different points in the line, we could find the slope pretty easily, which is the idea of a secant line, not a tangent line. So for example, here is a secant line going through the points P and Q. So we have a point x, and the point here is x comma f of x. X comma f of x. And the point here is a comma f of a. So the slope of that, the slope of the secant line would be f of x minus f of a over x minus a. So that's the slope of the line, which I'll trace here in green. It doesn't show up. Let me do a different color. I apologize. Along this orange line here. That's the slope. The slope of that line is what we're calculating on this calculation right here. Now the question though comes about what happens if I take the value of x and kind of walk it closer and closer to a. As q, the point moves closer along the path here, the line goes from where you currently see it to values, for example, in this region, even getting as close as things you might see along here. And these lines are traveling along this path, getting closer and closer to what we originally called the tangent line. So if we were to take the limit as x approaches a here of the expression seen right there, we would call the slope of the tangent line. This next graph again shows the idea behind it. If I've kind of taken that other point, moved it so close that it almost collapses on the point a f of a, which is still again attached right here. So it looks like a 9, doesn't it? A f of a is here and there. We get the idea of what's called the tangent line. So go back to the last slide just for a second. If we're iterating, we're looking at the slope of the tangent line being the limit of this expression here. We're getting the tangent lines that we intuitively understand as being the line that kind of just lines up with the curve here. So this slide has some information on it. I will let you pause the video and take notes if you wish, but it simply gives the values of things I mentioned before. This is the slope of the secant line as well as the instantaneous rate of change. Now we can throw in some notation here that this is what's called f prime of a. That is the slope of the secant line at the point x equals a. So this can be written in the bottom as y minus f of a equals f prime of a times x minus a, or as I prefer it, right, as y equals f of a plus f prime of a times x minus a. This here is the equation of the tangent line at the point a comma f of a. Here is simply an example. We have the curve of y equals negative 16x squared plus 96x. If we somehow knew the slope of the tangent at the point 180 was 64, I can create this equation here. Notice that if I put in 1 into this equation, I get that, I get that y when x equals 1 equals negative 16 times 1 squared plus 96 times 1, sorry for that, is 80. So we have the point 180 here. And if I know the slope is 64, I can write down that y equals f of 1, which is the 80, plus the slope at 1, which is 64, times x minus 1. If I clean this up, I get 80 plus 64x minus 64, or simply 64x plus 16, as you see right there. Again, I'll mention that where this came from here has not been divulged yet, but if you knew the value here, you can then make the calculation of the line shown here. This is the exact same as we had before, except we're going to change notation. The idea here is pretty simple. That we're going to let what used to be called x equal a plus h. Well, if I do that, then x minus a is the same thing as h. So in the denominator of the expression, I have simply an h. This is the idea to make the bottom much simpler. But this is now f of x minus f of a. Correct. And we then have the same image. We can look at the situation here, and I'll mention as, if x approaches a, that's the same thing as saying h approaches 0 because of the way that x and a are related. Again, h being close to 0, same thing as h being close to a. Sorry, if h being close to 0, same as x being close to a. Let's make that could go away. I apologize for the artifact there. This is some more information here. This is another way of looking at it with the new notation, same information we saw on a previous slide. And again, down here, I can use notation. This is f prime of a. Again, this is the derivative at the point, or the slope of the tangent line, provided the limit exists. We'll look at examples of where the limit doesn't exist in the next video. Another example here, if I have the function given as y equals x cubed plus 4x, and I know the point is 1, 5, and the slope is 7, I can use the formula mentioned before to get that y equals f of a, which is 5, plus the slope, which is 7, times x minus 1, which is 5 plus 7x minus 7, or simply 7x minus 2. Another calculation of the tangent line, assuming you know the value of the slope at the point. How to come up with this value here is still a little bit hidden, but we'll see that in the coming sections. This shows some ideas here. We're looking at a graph and getting a quick idea of what the derivative should be. The easiest point to see in this graph is likely the one at the top here, where the graph has a flat tangent, the top of the mountain. At that point, the tangent line is neither increasing nor decreasing, and we therefore get a value of 0 for the slope. Over here on the left side, the tangent lines are all increasing, and therefore we have a slope being positive. On the right side, I have functions which are tangent lines which are decreasing, which means all the tangent lines have negative slopes. This pushes the concept a little bit further. It now talks about this being a function. Recall that we had the idea that f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a over h. If I now were to come in here and remove the values of a, which were thought as being constants before, but now simply plug in values, or say variables x, I can let the value of x change to create not just a simple number, but a function, because as I change the value of x here, the limit will change. So this is now where x is here is the value there. Some more notation discussing different things. The two different notations used mainly for derivatives are the ones we've already mentioned, f prime of x down here, as well as one we'll see here, which is dy dx. This slide kind of shows the idea of where this notation comes from. If we look at the secant line being the change in y over the change in x, simply being your rise over your run, if I let the function have a limit where the delta x goes to 0, well, I have to kind of change notation because both the delta x and the delta y are 0. We simply say the deltas in the limit become the d's. Again, the Greek deltas are the Greek value, Greek letter which equivalates to 0, which is equivalent to d, becomes the normal d here on the right hand side. As always, if you have any questions, please feel free to contact me. Other than that, I will hope to hear from you guys soon. Thank you.